kinematics, while we were studying kinematics, kinematics itself is the study of motion without regards to the forces. We'll do the next units or so after this will be all about forces, but right now we're just talking about the mechanism of how things move, okay? Things that move, study of that is kinematics, okay? Forces is dynamics. So we're going to do kinematics first and then dynamics. Now, there are a couple of things we need to know. The example of vector versus a scalar. We need to know vector versus scalar, mostly because we need to know quantities. Not just quantities, but quantities and direction. So when we talk about a vector, we are looking at, as a vector, we're talking about direction and magnitude. Guys, an example of that would be velocity. It would be displacement. It could be force. A scalar is only a magnitude. Doesn't include direction. Things that have magnitude are things like mass, things like time. Believe it or not, time does not have a direction. Temperature, speed, distance. Now I want you to notice something. I said displacement here, but distance here. Now, I think we've already kind of talked about this in a little bit, but do you know the difference between a distance and a displacement? Yeah. Displacement has to do with where you started and where you ended. So there's a direction relative in there, isn't there? Distance is just how far you went all total. It doesn't matter about which direction you were going. It's just going to add everything up. Same thing goes with speed and velocity. Speed is just a magnitude. Velocity implies that you're talking about how fast you're going and also which direction you're pointing. I can go 50 miles an hour, and that is the speed. If I go 50 miles an hour towards Birmingham, that's now a vector. Get it? Because now I've specified a direction I am going. So now, what is a position? This is important. Where an object is located, it always seems so simple. Compared to a reference point. This is the important part. Where do we normally make the reference point that we're comparing it from? Where you start, which we usually call the origin. Guys, the cool thing is in physics is a lot of times we can specify where that origin is. We can say, okay, we're going to put 0 here. All right? Now, position in 1D kinematics. In 1D, we use position as x. In 2D, we use it as a point x, y. In 3D, guess what we would use? X, Y, Z, and so on. So now, displacement is a change in position. It is denoted as delta x. Delta means, it's the Greek letter delta, it means change. So anytime you see a delta in front of something, it means change. That is the final position minus the initial position. And guess what? Delta x is a vector. That's why we put a hat on top of it. This is a vector. However, distance is the length of path. So you're just going to add everything up, aren't you? The length of path is simply a sum. Okay? Notice what it says here about distance. What does it say about distance? Distance must always be what? Zero or positive. Can we have a negative distance? No, we can't, can we? If we start putting negative signs on it, that's direction. That makes it a vector. If I say you went negative 6 meters, I'm telling you, you went 6 meters backwards or in the negative direction. But the distance you went is still 6 meters, isn't it? Okay. So velocity. What do you suppose velocity is? Now, here's the difference, by the way. I'm just going to put this out here for you. If we say that this is x initial and we say this is x final, here's the difference. This right here is my displacement. However, that's my actual distance. If my path was like if my path was actually the black line, that path, if you measured all the different lengths of that path, that would be my distance. However, my displacement would simply be where did I start versus where did I end. So do you see the difference between the two? If I were to run around a track, start at the beginning, go all the way around the track, typical track is a quarter mile, isn't it? Right about that, a little more than a quarter mile, I guess, because they're now all measured in meters. Then my distance would be a quarter mile, but my displacement would be a big fat 0, because I started and ended in the same place. So are we good? All right. So now, velocity. Velocity is the rate at which displacement changes over time. In other words, v, velocity, is equal to the change in x, that would be my displacement, over the change in time. Change in position over change in time. It is a vector. Okay? Now, speed, however, is different. When we say my car is going 50 miles an hour, that is what we call an instantaneous speed. I'm reading the speed at that particular time, okay? So that's an instantaneous speed. So we need to know the difference between instantaneous speed and average speed. Instantaneous speed is, boom, I'm measuring where I'm at, how fast I'm going at that particular time. What we usually consider speed is what we call average speed. Okay? Average speed, which we typically call D for distance, right? Or, I'm sorry, S for speed. Excuse me, average speed is S. That is going to be equal to distance over the change in time. Okay? So do you see that this is a scalar? Distance is a scalar, isn't it? So we've got velocity, which comes from displacement, which is a vector. And distance, we've got speed, which comes from distance, which is a scalar. So a scalar produces a scalar, and a vector produces a vector. So far, so good? Yeah? Okay. So speed is the absolute value of the velocity. Do you understand why that is? If something's going, yeah, because the possibility of a negative, right? So if I'm going backwards at 20 miles per hour, I'm technically, my velocity is negative 20 miles per hour, but my speed is still 20, okay, miles per hour. So speed is often the absolute value of the velocity. So let's see what we got going here. Mario drives a go-kart around a circular track with a radius of 20 meters. What's his displacement? What's his distance traveled? What is his delta x? Good. Because he went around a circular track, we just talked about that. His displacement is 0. He started and ended in the same place, didn't he? However, his distance, how do we measure his distance? Okay, what formula? It's a circle, so how do we measure the distance around a circle? Circumference, and what's the formula for circumference? 2 pi r. So his distance is going to be 2 pi times the radius of the track. So we do 2 pi times the radius, which was, so this is 40 pi meters, which in real world we would say is what? 120 something. What is 4 times pi? 40 times pi. Mm-hmm.
Isaac Castaneda?
Not here.
He's not here. Okay, thank you.
Mm-hmm. Oh, speaking of, I better do my yell at me.
What's after that M?
Where?
That's like a squiggly equals.
Approximately.
Yeah.
Hmm.
I didn't know.
Yeah.
That's what it's basically.
Maybe she won't yell at me now. Okay. So let's keep going here. So this was B. The distance he traveled, 125.6 meters. Okay, thereabouts. Okay. Under what conditions will an object have a distance equal to its displacement? Talk this over with your table partner. When will the distance and the displacement be the same?
When they end up. When they only go, when they go in a straight line
Travel a distance.
and they don't go backwards.
Yeah.
And they.
Good. All right. So, did everybody come up with the fact that when it's only moving in a positive direction, in a what? Straight line. Okay. Why do I have to specify forward? Yeah. Backwards would give a different displacement, wouldn't it?
Yeah.
Could be negative. Okay, so we have to say it moves forward, and forward is a positive direction, right? Positive x direction in a straight line. All right, so let's bring that into play. Look at example C. It says Pikachu and Eevee are both located at the origin. At time t equals 0, they both start moving. Pikachu moves with a velocity of 20 meters per second. Eevee moves with a velocity of negative 10 meters per second. Find the distance between the two after 10 seconds.
Going backwards.
Backwards 10 meters per second.
They move fast.
Mm-hmm. Oh, they're Pokemon. So the strategy here ought to be to find the distance each one of them moved, right? And we know distance must only be what? positive. So we're going to find each distance, and then we're going to do what? Add them together, right? Now, if you made a little graph of this, if this is 0, Pikachu's moving this way, isn't he? 20 meters per second for 10 seconds. This is 200 meters, isn't it? Evie's moving this way, but she's only going 10 meters per second. And now I don't have to put the negative with it, do I? Why?
Because it's an absolute value.
Because it's absolute value, and I've shown it in the picture that she's going the other direction, doesn't it? Isn't that what the negative means? Is she's just going that way for 10 seconds. So this is 100 meters. So what is the total distance between those two after?
300.
Yeah. 200 plus 100 is 300 meters. Now what if they were both going in the same direction? What would be the distance between them? Yeah. Why 100? Yeah. She's going the same direction as him, then she would just be going a little slower, wouldn't she? So you'd have to take the 200 and subtract off the 100 she went. All right, so acceleration. Acceleration is the rate of change of velocity. Is velocity a vector? Yes. So is acceleration a vector? Yes. So acceleration is a vector. So we write acceleration is equal to, that little hat means vector, by the way. Change in what? Delta V over delta T. Rate of change of velocity, we're always dealing with time, aren't we? So now we've got to pay attention to signs. If velocity and acceleration are in the same direction, the object must be speeding up. Now, why do I have to imply in the same direction? If I'm driving my car and I push it forward and I push down on the gas, I'm accelerating it in the same direction, aren't I? What's going to happen to my car? It's going to speed up, isn't it? If I throw it in reverse and I'm going and I press down even harder, what am I going to do? I'm going to go faster that way, aren't I? So the acceleration is going in the same direction the car is already moving, so it's going to go faster. Now, the brake pedal, which we call decelerating, is the decelerator. The brake pedal acts as acceleration, but in the opposite direction. So if I'm driving and I take my foot off the gas and hit the brake, I'm applying acceleration, but I'm going this way, I'm speeding this way, but now what's happening to my car? Slowing down because my acceleration is going in the opposite direction. So if I'm going forward, but my acceleration is backwards, my car is slowing down. But it's the same way. If I'm going backwards and I hit the brakes, it's still slowing down, isn't it? So I'm applying the force in the opposite direction. I'm applying the acceleration forward. So as long as these are opposites, it's slowing down. If they're the same, I am speeding up. Okay? All right. So if acceleration and velocity are in the same direction, the object is speeding up. And if velocity and acceleration are in the opposite directions, it is slowing down. Which means you have to pay attention to signs now. If my velocity is positive but my acceleration is negative, that means it's getting slower. If it is opposite that, if they're both positive or both negative, it is getting faster. Now, we can actually take this right here and see that this is going to be final velocity minus initial velocity divided by time, right? I can manipulate that equation, believe it or not. I can actually manipulate this equation and come up with an equation that says this. My final velocity is equal to my initial velocity plus the acceleration times time. Can you tell how I got there? What did I do? I took the t and I cross-multiplied it over here, didn't I? Yeah? T, crossed it over here. So then I had v final minus v initial, and then I added v initial over as well. V initial. I started this fast. I accelerated. So do you get why the signs work here? If this is positive and this is positive, it's going to add up, isn't it? Which means my final velocity is getting bigger. If this is positive, but this is negative, it's going to subtract away, which means the velocity, final velocity would be lower, wouldn't it? So do you see how the signs work in this equation, if we look at it in that form? All right. Family excitingly drives to Home Plus for some well-choreographed shopping. For each of the following cases, determine the direction of the acceleration of the car. In other words, they want to know north, south, east, and west. Talk with your table partner and tell. If the car travels east and is speeding up, what direction is the acceleration? What direction must it be in? Mm-hmm. Yep. Has to be in the same direction it's traveling in, doesn't it? So east. Travels east and slows down.
West.
Good. Travels east at a constant velocity.
East. It's in place. Wait, no.
Direction of the acceleration.
There's no acceleration.
Haha! Nice. Acceleration is
0.
has to be 0 because otherwise it's either got to be speeding up or slowing down. So in this case, the acceleration is 0. There is no acceleration if it's speed staying constant. Car travels west and slows down. Good. Acceleration is eastward. Car travels west and speeds up. West. Y'all got this. See, this is not so bad. All right. For an object in motion, there are 5 primary kinematic quantities to describe the motion. V initial. Now, I want to make some changes here. I want you to look at the purple sheets in the wells. Take a look with your table partner. You're going to see some differences in notation. I use V initial, V final. They don't use those. They use V initial. They use this, V naught. Okay? Look at the very first equation. V sub x equals, where it says mechanics. V sub x equals V sub x naught plus AT, A sub xt. They don't use F for final. Delta x, they don't use delta x. But there is an implied delta x on your sheet, okay? A for acceleration is the same. The sub x just tells you the direction. These are for one dimension, so it's saying in the x direction. A sub y would be acceleration in the y direction, wouldn't it? I don't want you to get confused between the formula sheet and what we're doing here. And delta t is time. Normally, they don't use delta t, they just use t. T is the change in time, okay? So let's look at these equations.
We're supposed to mark everything out too.
No, I'm just telling you, I'm going to do them both ways. When we're given a problem and there is no acceleration, we want to find, there's only one thing we can do with no acceleration is find our distance. We don't know what the acceleration is. We don't know how fast. We can just find an average of how far we think it's gone. So it's an average distance, okay? This is this. Delta x equals V initial plus V final over 2 times t. This is not on your formula sheet. This is the only one that's not on your formula sheet. You take the average velocity over that period of time and you divide it by, or you multiply it by the amount of time. Do you get why we say average velocity? Isn't this an average? We take the initial and the final, we divide it by 2. We don't know. See, here's the thing. If we don't know the acceleration, we don't know if it's sped up, slowed down, sped up, slowed down. We don't know what it was doing, did we? So all we can do is say, we know at this point, over this period of time, it was going this fast to this fast. That's all we know. So we're going to average that out, and we're going to multiply it by the amount of time it took to get that, to over that speed, that we were at that speed, and that's going to give us about an average of how far we went. Make sense? Okay. No displacement. If we don't know the displacement, These are qualified by what you don't know. V final equals V initial plus AT. Now this one is on your sheet. Your sheet lists it as V equals V naught plus AT. So that is V final. V is V final. V naught is V initial. Naught means at the beginning, not as in 0. Okay? This is the one that's actually on your formula sheet that you should be able to recognize. Okay? Now, change in, the next equation is delta x. The change in position, that would be delta x, wouldn't it? Equals V initial t plus 1/2 AT squared. Now that is not how your formula sheet writes it. Your formula sheet writes it this way. X final equals where you started X initial plus V initial t plus 1/2 AT squared. This is what's actually on your formula sheet. Okay? Oops. That's what's on your formula sheet. Do you understand where the delta x comes from that I use? Delta x would be the changed position. This would be x final minus x initial, wouldn't it? What would happen if I took this and moved it over to this side? It'd be minus, wouldn't it? So this minus this is what gives me this over here. So please just understand that this and this is actually on your formula sheet. This is the same thing as that. Okay? We can find the change in position if we know everything. Do y'all notice what we don't know is the final velocity in that equation? That equation does not require the final velocity, does it? There is no V in that, V final in that. All right, so what's the next one? No initial velocity. That's fine. We could do delta x. Ooh, excuse me. We could do delta x equals V final t minus 1/2 AT squared. Do you see why this gives you, why if we use the final velocity, this one's not on your formula sheet, but does it make sense to you? If we know how fast we were at the end, and we subtract away how much we accelerated, wouldn't that give us how fast we were going in the beginning? That would give us our position. So since it was V final t, we did minus 1/2 AT squared. Now, if we don't have time, there's only one equation of all the kinematics equations, what we call the big five, that does not include time. That is the third equation on your sheet. It says V final squared equals V initial squared plus 1/2 2, excuse me. Just had a little brain burp there, plus 2a delta x. Now, this is not what your formula sheet reads. Your formula sheet reads this way. V squared equals V naught squared plus 2a times x minus x naught. Do y'all see that's the same thing? This is x final minus x initial, isn't it? Isn't that delta x? V final just writes, they just write anything final is just a variable, and V initial is V naught. Okay? This, and this are the three equations on your formula sheet that you will be given on the test. Okay, when you take the exam. These three. So the cool thing is you don't have to memorize those. You get this with every test you take in here. As a matter of fact, I suggest you have this out. I gave you a copy of this, didn't I? In the very first day? I thought I gave you one that was white. In your initial stuff, I thought I gave you a formula sheet. A set of formula sheets. You got a lot of stuff that day, I know. If I didn't, I need to know because I need to make you one.
We didn't get one.
I'll get you some next time. I'll get you some folders. I'm sorry. So that you have a set that you can use at home. These are always here, so when you take tests, you know, and I color code them so you know which one. I've got 3 different APs so you can figure out which one's yours. All right. Questions so far? We still good? All right, so let's do these and let's figure out how we use these. Guys, kinematics, these formulas, these big 5 formulas, only work if we have a constant acceleration. These don't work if we're going fast, if we're changing our acceleration. They only work with constant acceleration or uniform acceleration. Uniform acceleration is the big deal. If the acceleration is not uniform, we cannot use kinematics. Okay? Now you know why we suddenly will change to doing dynamics. Guess what dynamics means? The acceleration is changing. So next unit, we'll look at these from the standpoint of what happens when we aren't accelerating uniformly. So for now, we've got easy ones, okay? So how do we solve a kinematics equation? How do we solve a problem? You want to list your knowns. Okay? List your known quantities and your unknown quantities, right? Hopefully there's only one unknown quantity. Then you're going to figure out which kinematics equation am I going to use. Then you're going to plug in your values and solve for your unknown. All right. We got time for one example here, or two, and then we're going to, we obviously are not going to get through all of this today, but we did get through 1-1. So you do have your 1-1 practice problems to do. Just not 1-2, okay? Because we won't get all the way through 1-2. Yeah. 1-1, just do the 1-1. I gave you all of the notes and all of the homework for this unit today, okay? But just 1-1 practice. All right, so let's get through this one. Hyundai Elantra uniformly accelerates from 12 meters per second to 20 meters per second in 3 seconds. What distance did it travel? So let's do step 1. Let's list what we know. What is this right here telling me? Initial velocity. So V naught is 12 meters per second. Okay, what does this tell me? V final. So V is 20 meters per second. What does this tell me? Time is 3 seconds. What distance did it travel? So what is it asking for there? Distance it traveled means we are looking for delta x, aren't we? How much did the distance change? Okay, so now we have to pick which equation we're going to use. What are we missing here? What do we not have here? We don't have we're looking for the distance, but we don't have we have velocities. Yeah, we don't have the acceleration, do we? So which one of these equations does not have acceleration?
Delta X.
Yeah. So that's the one we have to use, guys. Delta X equals V final plus V initial divided by 2 times the time, doesn't it? So what are we going to do with the two velocities? Atom. 12 plus 20 divided by 2 times what? 3 seconds. Gives me a change in position of what? So that's 32 divided by 2 is 16 times 3 is 48. 48, and make sure you use units, meters, right? Our units in physics are meters, kilograms, seconds, but in meters. All right. So we're going to pick up here next time. We'll pick up here and keep on going. But you do 1-1 practice, right? 1-1 practice before next time. All right, guys. Good job. You did a really good job today.